fortunate enough to receive a grant from the Green Music Center to buy an acoustic measurement system so that we can characterize the various buildings and start a small acoustics program here in the physics department. And last year we were lucky, we had one student whose capstone project is measuring wild hall. And this year Thomas Kohlmeyer, who I'm introducing now, worked on measuring the just finished or recently finished Schroeder Hall, which we thought might be a little more interesting. And so he's going to talk about his research in the acoustics of Schroeder Hall.
Dr. Jones, and as he said, I'm Tommy Kohlmeyer, and I did acoustic analysis of Schroeder Hall and actually another classroom as well. So my goals coming into this was to create an acoustic map of Wild Hall. And then as we started working through calibrations, we realized that Wild Hall really, it's such a great hall and there's such little variance that a map of that hall probably would not be that interesting. And like we already have the overall data of it. So decided to do a sound map of the Schroeder Hall. And then do a comparison as well. And for anybody who doesn't know, Schroeder Hall is right here in the Green Music Center. And the reason we thought it might be more interesting is the stage is up front on both these halls. Left side is Schroeder Hall, right side is Wild Hall. The Schroeder Hall has, I don't know if there's some mid walls, but they're much harder walls along the outside here that are very reflective and reverberant in the back. So we were interested to see what happens to the sound as it gets farther back into the room, as well as how that affects the front of the room. Okay, and then there are many parameters that have been accepted by ISO, the International Standardization Organization for analyzing acoustics. And I decided to choose just 3 that I thought were pertinent: early decay time clarity and lateral energy fraction. And early decay time is the time it takes for the sound intensity to drop by 10 decibels. And it corresponds to the reverberance in the room. And typically you'll get values between 1 and 3 seconds. And Wild Hall showed that it was basically right in the middle of that range. And clarity is kind of exactly what it sounds like. But it's the ratio of the early arriving sound energy compared to the energy that arrives later, 80 milliseconds later. And typically, you'll get values between -5 and 5 decibels. And lateral energy fraction, that is the ratio of the sound that's coming from the sides compared to basically anything direct with a omnidirectional microphone will pick up all that noise, and a bidirectional picking up from side to side. And you'll typically get 0.05 to 0.35 for any normal hall. And yeah, of course, it's kind of helps you find the source of the sound. And then here are the formulas. There's LF here is the lateral energy fraction, C80 is the clarity, and EVT is up there. Don't need to understand the formulas. So Jacob Lewis last year found that Wild Hall has very great EVT times between 1.8 and 2.2 seconds, and they don't vary very much as you go between different frequencies. Because that's key. As you move through different frequencies, how the sound changes for all these frequencies. And the clarity's at the lower end, but that's kind of to be expected, and it fits in with some of the world's most renowned halls. I'll be mentioning there's halls in Boston and Vienna that we kind of treat as the standard for all of these values. And then it had low lateral energy fractions, but that's acceptable because it's a big hall and it's basically fits in with what we see in Boston and Vienna, all these halls. So here's my system. I don't know what happened to my original image. This triangle should be going the other way. But there's a USB that hooks into your computer, the digitizer here, and you send an output signal out through the speaker, and then it is picked up by these 2 microphones, one omnidirectional and one bidirectional, and then it runs back into your through the digitizer into your computer to analyze it. Here's some of the equipment I used. It's mostly Kohlmeyer and you have the omnidirectional sound source, which is there. That's only the omnidirectional microphone, but I believe there's a picture of the bidirectional later. That's the only one that's not Kohlmeyer. So important. But here's the early decay times that we have found. This is kind of hard to see. Like number 1, we have Schroeder Hall. 2 is Wild Hall. And we'll just focus on Boston. Number 4, and Vienna is 8. So you see for the EDT times, surprisingly, they kind of fit into a lot of these ranges, but as you go to higher frequencies, they drop off pretty heavily. Whereas Wild Hall, right here, kind of sits in that same range the whole time until you get a little bit of drop off at 4,000 hertz. And then, as you can see, Boston and Vienna are pretty homogeneous as you move through it as well. There's a little rise there, 2,000 hertz. But then here are the maps I made of the hall. The red dots are all of the data points. They're meant to be pretty symmetrical, but there's a couple spots that are missing out. And this area right here, between 10 and 15, is a row of a break in the seating where that's basically just an aisle you can walk through. So we didn't take data there because it's not pertinent to listeners. So you can see the early decay time. It's pretty homogeneous as you move like anywhere in the hall, but as you change frequencies, the early decay times will drop. The red is the higher end of the range, and it will be for all of these sound maps, and the blue is the lower end of the range. The white is in the middle. So you can see as you move through, the 1000 was kind of white, and I have about 21 of these maps, and if people want to see it, have it available to you at any time, but thought that'd be a little bit of overkill. So yeah, there's that small shift as you move over. And then they actually, as I said, they match those seen in many other halls. There's little to no dependence on seating. And the short distance between the walls, because Schroeder Hall is so much smaller than all of these other halls we've been talking about. The sound hitting the walls has a smaller distance to go between the walls. So it plays a huge factor in how long the reverberation is able to last. Okay. And then clarity, this is against all the other halls. You can see that it starts off kind of in the normal range, and then as you go to higher frequencies, it increases greatly. And that's almost opposite of what we saw with the EDT times, and that makes sense, or the EDT times, and that makes sense because the longer reverberation times for the lower frequencies will interfere with the waves at the lower frequencies, so you will have less clarity. Point out Wild Hall as well. Wild Hall is pretty homogeneous as you move through, and so are Boston and Vienna, where we have this huge range for Schroeder. And then there's more seating dependence here, as you can see at low frequencies. The very front, you have okay clarity, but it's lost in the whole middle area. At the epicenter, it's the epicenter right here of the semicircle in the back of the room. There's higher clarity, and we thought that was kind of everything coming together, and it's just a strange point where wouldn't really want to sit around the epicenter, but there's a little area where you have higher clarity at that frequency. And then at 1,000 hertz, kind of middle frequencies, it's just middling range. And then at the very high frequency, if you sit in the front of the room, you have great clarity, and as you saw, it's higher than almost any other hall that was measured in that chart. As I said, inverse relationship with early decay time and small dependence on seating charts, front of the room side. The lateral energy fractions. This is where we get some exciting data. So all of these halls are kind of sitting here. As I said, the normal range is 0.05 to 0.35. All of them fit in this range except for us, or Schroeder. So that is above 1, which means that the sound energy you're getting off of the walls is higher than what you're getting directly from you, and because it's omnidirectional, it's actually including some of the sides. So that means you're getting a huge amount of sound energy from the sides. But then when you get to lower frequencies, where you have, or higher frequencies, as you get closer to where we have higher clarity, that kind of drops off. And the sound maps, this is kind of a strange point. I kind of think that's just an anomaly for near the back of the room. But so we have and these are all compared to each other. So it makes this look like this is low lateral energy fractions, but these are actually very high in all of these charts. So you have high lateral energy fractions in these seats along the side and at low frequencies, and you can definitely hear that when you're there. It's much more energy bouncing off the walls, and it almost ruins where you believe the sound source to be coming from, because you have this sound coming here, and then there's almost more noise just coming straight off the wall if you're in, like, say, the three seats along the side. So, as I said, extremely high in general. The walls are extremely solid, but also rough. So it makes sense that the smaller wavelengths or higher frequencies would scatter off of the walls more, and the longer wavelengths would just reflect off. So you'd be getting those higher lateral energy fractions. And then, so the Hall acoustics appear to be much more dependent on acoustic frequency than seating location, which is surprising to me because when we did the analysis, it's kind of hard to perceive what you're getting when you see these values just once, but then you put this map together and you see that it's actually pretty homogeneous throughout the seating, other than those lateral energy fractions along the sides. And as I said, there's a compromise between clarity and delay time because they're directly related, and it's very difficult to build a hall with the uniform reverberation of a large hall like Wild when you have your walls right next to each other and high reverberance. But that's kind of what the hall was built for because it's mostly used for choral, organ, and acoustic performances. So I think if you went in there and tried to play a rock concert, everything would be so muddy because you'd have stuff bouncing off the walls, you wouldn't even know where the performance is coming from. But it works for what it does, or what it's meant to do. And lateral energy fractions above 1 is almost ridiculous. But it's very interesting to see. As I said, it's difficult to locate the source. And there's endless research possibilities for the future. I was thinking, I do have a bunch of data from a classroom in Darwin basement that I didn't have the chance to make a map for, but it'd be nice to compare that to other classrooms on campus that are older, or compare that to other classrooms, including classrooms in Ives and classrooms that are acoustically treated in the Green Music Center. And the development of an omnidirectional speaker, I think Dr. Jones is going to be working on in the future, that actually recreates live performances rather than just shooting out frequencies. And thank you. I'd just like to thank Dr. Michael Jones. Steve Anderson wouldn't be possible without you. Thank you so much, my parents, and Jacob Lewis for his work. Any questions?
So for the lateral sound fraction, lateral energy fraction?
Yeah.
So if it's greater than 1, does that mean you're getting more energy when you push into it? Or
No.
what does that mean?
Yeah, in a way, because it's bouncing off the walls like so much that it's coming back. You're getting energy that bounces off the walls and hits you, but then you're getting it bouncing off the wall, coming back and hitting you. So it's not that you're getting more off of one wall than you have coming at you, but there's so much reverberance at those frequencies.
So they're adding together.
Yeah, exactly. Dr. Knitzy?
So we've been teaching a big astronomy lecture class in Schroeder Hall.
Oh, have you? I was actually
Not
wondering.
me, but Wes Ferris, and so I was wondering what you would, recommend to students that might be trying to listen to a lecture class in Schroeder.
Dr. Jones and I were actually talking about this the other day. Like, if we did poetry readings in that hall, it has to be very hard to hear, especially as you move farther into the room. So I can only assume that that's not a good thing for lectures or anything like that. It has to be much higher frequencies for it to be clear.
That was my question. But I had another one, which is it spacious? Would it feel spacious to have the sound coming from all? You said that there's a way that you can't locate it. I mean, what are descriptive terms to sort of describe what you think the sound in there is like?
I would almost say that spaciousness would be not a lack of lateral energy fraction, but much lower ones, because then you understand that there's sound coming off the walls. There's always going to be sound coming off the walls when you're inside, but you are able to locate the source, so that spaciousness, in a way, is inversely related to it. Any other questions?
What's the best seat in the house?
Best seat, front and center. That's mine. Or in the epicenter of that semicircle in the back, I thought it had some positives and some negatives. But it seemed like a good seat as well.
Did you take into account the shape? They both looked like they were different shapes of the halls. Like you said, the one has a curve. How does that affect the sound? Did you look into that at all?
I think that just came into our data. We didn't really take it into account in how we measured it or anything, but I think it shows that as you get into the back of the room, that there were those distortions, and I think it was clarity. That there were distortions in the back of the room. My graphs are just an XY plane that is not square but a rectangle, so it doesn't quite show it, but that curve is included in the back of the graph. So when you look at that data, you see that effect. But we didn't change anything in order to measure it.
Are you going to take acoustic analysis into your professional? And if so, would you work with the architect or the artist?
Probably not, because I've been thinking of electrical engineering, electronics.
Let's pretend you were going to take acoustical analysis into your
Then I would probably say architect.
You'd work with an architect to do this?
Because it's interesting. There's a lot of research being done on how all these different parameters, people are trying to change the perceived parameters, and people are trying to change. It's well known that the shoebox design of Weill Hall and Boston and Vienna is like basically the best we have at this point. But there's a lot of research being done to see like what we can do to improve anything. Like classrooms, there's a lot of thought being put into how we can make things more clear for people hard of hearing. Actually be interested to see somebody or me work with that classroom data and see in the corners at the back of Darwin Hall basement, do people lose clarity there? Like, are people in the back who sit in the back, do they actually miss out on something when they rather
Or
than
maybe
sitting
they're
in front?
getting more. Yeah.
Yeah. So that research needs to be done.
That's good. Good research.